Learning objectives. In this chapter, the user would learn the following in detail. Limitations of current IP networks. Internet Protocol version 6 IPv6 features. IPv6 extension header. Quality of service in IP. Integrated Services Architecture ISA. Process sharing. Weighted fair queuing WFQ. Random early detection RED. Differentiated services. Differentiated services. Differentiated services model, often called DiffServ for short, allocates resources to a small number of classes of traffic. The IETF standardized a set of router behaviors to be applied to marked packets. These are called per-hop behaviors, PHBs, a term that indicates that they define the behavior of individual routers rather than end-to-end services. Because there is more than one new behavior, there is also a need for more than one bit in the packet header to tell the routers which behavior to apply. The IETF decided to take the old TOS byte from the IP header, which has not been widely used, and redefine it. 6 bits of this byte have been allocated for DiffServ code points DSCP, where each DSCP is a 6-bit value that identifies a particular PHP to be applied to a packet. Expedited Forwarding EF PHP. One of the simplest PHBs to explain is known as Expedited Forwarding EF. Packets marked for EF treatment should be forwarded by the router with minimum delay and loss. The only way that a router can guarantee this to all EF packets is if the arrival rate of EF packets at the router is strictly limited to be less than the rate at which the router can forward EF packets. The rate limiting of EF packets is achieved by configuring the routers at the edge of an administrative domain, allow a certain maximum rate of EF packet arrivals into the domain. Ensure that the sum of the rates of all EF packets entering the domain is less than the bandwidth of the slowest link in the domain. This would ensure that even in the worst case where all EF packets converge on the slowest link, it is not overloaded and can provide the correct behavior. There are several possible implementation strategies for the EF behavior. Give EF packets strict priority over all other packets. Perform weighted fair queuing between EF packets and other packets with the weight of EF set sufficiently high that all EF packets can be delivered quickly. Performing WFQ has an advantage over strict priority. The non-EF packets can be assured of getting some access to the link even if the amount of EF traffic is excessive. This might mean that the EF packets fail to get exactly the specified behavior, but it could also prevent essential routing traffic from being locked out of the network in the event of an excessive load of EF traffic. Assured Forwarding AF PHP. The Assured Forwarding AF PHP has its roots in an approach known as RED with in and out, RIO or weighted read, both of which are enhancements to the basic RED algorithm. RIO calls the two classes in and out since the out curve has a lower minimum threshold than the in curve. It is clear that under low levels of congestion, only packets marked out will be discarded by the read algorithm. If the congestion becomes more serious, a higher percentage of out packets are dropped, and then if the average queue length exceeds minimum in, the read starts to drop in packets as well. figure read with in and out drop probabilities. There must be enough bandwidth in the networks so that the in packets alone are rarely able to congest a link to the point where Rio starts dropping in packets. Just like read, the effectiveness of a mechanism like Rio depends to some extent on correct parameter choices, and there are considerably more parameters to set for Rio. Rio does not change the order of in and out packets. This is important for most TCP implementations, which perform much better when packets arrive in order, even if they are designed to cope with misordering. Rio can be generalized to provide more than two drop probability curves, and this is the idea behind the approach known as weighted read WRED. In this case, the value of the DSCP field is used to pick one of the several drop probability curves so that several different classes of service can be provided. A third way to provide differentiated services is to use the DSCP value to determine which queue to put a packet into in a weighted fair queuing scheduler. As a very simple case, we might use one code point to indicate the best effort queue and a second code point to select the premium queue. We then need to choose a weight for the premium queue that makes the premium packets get better service than the best effort packets. This depends on the offered load of premium packets. B premium is equal to W premium by W premium plus W best effort. The delay experienced by the premium class can be kept low since WFQ will try to transmit premium packets as soon as they arrive. On the other hand, if the premium traffic load were 30%, it would behave like a highly loaded network, and delay could be very high for the premium packets, even worse than the so-called best effort packets. Thus, knowledge of the offered load and careful setting of weights is important for this type of service. Just as in WRED, we can generalize this WFQ based approach to allow more than two classes represented by different code points. Furthermore, we can combine the idea of a queue selector with a drop preference. IPv6 extension headers. Extension header. The IPv4 header has space for some optional fields requiring a particular processing of packets. These optional fields are not used often, and they can deteriorate router performance remarkably because their presence must be checked for each packet. IPv6 replaces optional fields with extension headers. Extension headers are based on the principle that most of the packets need a very simple processing, and therefore basic fields of the IPv6 header are sufficient. Packets requiring additional information at the network layer can encode this information in additional headers that can be placed in a header between the IPv6 header and the upper layer header. An IPv6 packet can have no extension header, one extension header, or several extension headers. Each extension header has a length equal to a multiple of 8 octets, 64 bits. Figure extension header. A full implementation of IPv6 must include support for the following extension headers: hop-by-hop options, routing type 0, fragment, destination options, authentication, encapsulating security payload. Extension headers order. Extension headers must be processed in the order they appear in the packet. Most extension headers will be processed only by the destination node. Therefore, they do not affect the router's performance. The only type of extension header to be processed by all nodes along its delivery path is the hop-by-hop options header, which, if present, must immediately follow the IPv6 header. Its presence is indicated by the value 0 in the next header field of the IPv6 header. When more than one extension header is used in the same packet, the headers appear in the following order: IPv6 header, hop-by-hop options header, destination options header, see note 1, routing header, fragment header, authentication header, encapsulating security payload header, destination options header, see note 2, upper layer header. Options. Among extension headers previously listed, the hop-by-hop options header and the destination options header carry variable numbers of options. These options, which are encoded in a format called TLV, type length value. The three fields that appear in the described option have the following meanings. Option type is an 8-bit unassigned integer. It defines the type of option. Option data length is an 8-bit unassigned integer that contains the length of the option data field in octets. Option data is a variable length field that contains the option type specific data. In particular, the two highest order bits action specify the action that must be taken if the processing IPv6 node doesn't recognize the option type. These bits can have the following values: 00, skip over this option and continue to process eventual subsequent options. 01, discard the packet. 10, discard the packet regardless of whether the packet destination address is multicast. The source node is notified by an ICMP packet. 11, discard the packet and only if its destination address is not multicast, the source node is notified by an ICMP packet. Figure. Detail of the option type field. The third bit C change specifies whether the option data can change en route to the packet's final destination. 0. Option data cannot change en route. 1. Option data can change en route. Two padding options are used when necessary to align subsequent options. The A option, which is called pad 1, is used to insert 1 octet of padding into the options area of a header, and the B option, which is called pad n, is used to insert 2 or more octets of padding in the options area of a header. Hop-by-hop options header. The hop-by-hop options header is used to carry optional information that must be examined by every node along a packet delivery path. This type of header must immediately follow the IPv6 header, and its presence is identified by a value in the next header field of the IPv6 header. The 8-bit next header field has the same meaning as the fields with the same name in the IPv6 header. The 8-bit HDR-EXT-LEN header extension length field contains the length of the hop-by-hop options header in 8 octet units, 64 bits, not including the first 8 octets. Expressing the length this way can appear extravagant, but it speeds up IPv6 implementations. In fact, remember that extension headers have lengths in multiples of 8 octets, 64 bits, and they obviously cannot be empty. Therefore, they are almost always 64 bits long. The options field has a variable length and it contains one or more TLV options. In addition to the pad 1 and pad n options, we will define the jumbo payload option. Figure hop by hop options header. The jumbo payload option. The choice to have a 16-bit payload length field limits the IPv6 payload length to 65,535 octets. The jumbo payload option can be used to exceed this limit. This option requires a 4n plus 2 alignment where n can be any natural number. This means that the option can begin with octets 2, 6, 10, 14 and so on. The format of the jumbo payload option is shown in figure 3 to 7. The 8-bit option type field contains the value 194, which indicates the jumbo payload option. The 8-bit option data length field contains the value 4, which indicates that 4 octets of data will follow, that is, the jumbo payload length field. The last one indicates the packet length in octets, excluding the IPv6 header but including the hop-by-hop options header. This length must be more than 65,535 octets. The payload length field of the IPv6 header must be set to 0 in every packet that carries the jumbo payload option. The jumbo payload option is not consistent with the fragment header. Therefore, they cannot be present in the same IPv6 packet. If an IPv6 implementation doesn't support the jumbo payload option, it cannot have an interface to a link whose link MTU is greater than 65,575 octets, 40 octets of the IPv6 header plus 65,535 octets of payload. Figure the jumbo payload option. Routing header. The routing header is used by an IPv6 source to specify a list of intermediate nodes that a packet has to traverse on the path to its destination. The specification can be for each node on the path binding strict or not loose. The routing header is identified by a next header value of 43. The 8-bit next header field uses the same values as the field with the same name in the IPv6 header. The 8-bit HDR-EXT-LEN header extension length field contains the length of the routing header in 8-octet 64-bit units, not including the first 8 octets. In case of a type 0 routing header, the HDR-EXT-LEN value must be less than or equal to 46, equal to twice the number of addresses in the header itself, and therefore even. In fact, the first 64 bits contain the fixed part of the type 0 routing header, next header, HDR-EXT-LEN, routing type, segment left, reserved, and strict loose bitmap, and each address has 128 bits, that is, 2 times 64 bits. The 8-bit routing type field always contains, in this case, the 0 value. Different values can be used in the future to support new types of routing headers. The 8-bit segment left field contains the number of explicitly listed internodes still to be visited on the path to the destination, that is, the number of addresses not yet used. The maximum legal value for this field is 23. The 8-bit reserved field is reserved for future uses. It must be set to 0 for transmission and ignored on reception. The 24-bit strict loose bitmap field is a mask containing a strict loose bit for each address. If the strict loose bit associated with an address is 0, then the address must be treated as loose. If equal to 1, the address must be treated as strict. Each address field is 128 bits long and up to 23 address fields can be used. They contain IPv6 addresses of nodes to be traversed along the path to the destination. Nodes are visited in order address 1 to address n. When a routing header is processed by a node, the node checks whether the segment left field is different from 0, and if so, it extracts the following address and the strict loose bit associated with the address. If the bit indicates that the address must be treated in the strict way, the node checks that the address belongs to an adjacent node, a neighbor on one of the links, and it delivers the packet on the interface associated with that adjacent node. If the node is not adjacent, the packet is discarded. If the bit indicates that the address must be treated in the loose way, the node examines its routing tables and routes the packet to the address. Figure: Type 0 routing header. Fragment header. The management of fragmentation in IPv4 is rather different from the management in IPv6. In fact, one of the IPv4 router's tasks is to fragment a packet if its size is too large to fit the MTU of the link on which it must retransmit the packet. For example, if an IPv4 router receives a 4000 octet packet from an FDDI ring and must retransmit it on an Ethernet network with an MTU link of 1500 octets, the router fragments the packet into 3 packets with sizes less than or equal to 1500 octets. The IPv4 function can be deactivated by setting the don't fragment bit to 1 in the IPv4 header. IPv6 routers can always operate as if the don't fragment bit were equal to 1. When they receive a packet whose size exceeds the MTU link, they discard the packet and signal this fact to the source through an ICMP packet by indicating what is the maximum length that can be accepted for the packet. The source node will appropriately fragment the packet before retransmitting it. The fragmentation can be implemented in IPv6 only by the source node through an extension header and in particular by a fragment header. The fragment header is processed only by the destination node and ignored by nodes along the path. The fragment header is identified by the value 44 in the next header field. Figure: Fragment header. The 8-bit next header field uses the same values as the field with the same name in the IPv4 header. The 8-bit reserved field is reserved for future uses. It is initialized to 0 for transmission and is ignored on reception. The 13-bit fragment offset field contains the offset of the data following this header relative to the start of the fragmentable part of the original packet before fragmentation in 8-octet 64-bit units. The 2-bit res field is reserved for future uses. It must be set to 0 for transmission and ignored on reception. The 1-bit M more fragments field indicates whether a fragment is the last in a packet. M is equal to 0 or not. M is equal to 1. The 32-bit identification field contains a unique identification of the packet generated by the node that executes the fragmentation. Its aim is to simply identify all fragments belonging to the same packet. The fragmentation process. An IPv6 packet consists of a fragmentable part and an unfragmentable part. The unfragmentable part consists of the IPv6 header plus other headers that must be processed by all nodes along the path, that is, extension headers up to and including the routing header. The fragmentable part consists of the rest of the packet, that is, extension headers that must be processed only by the destination node and the IPv6 payload. This part is divided into fragments that are multiples of 8 octets, with the possible exception of the last one. A fragment header is put before each fragment, and fragments are transmitted as separate IPv6 packets. The unfragmentable part, which is repeated in each packet, is equal to the original unfragmentable part with 2 exceptions. The payload length field of the IPv6 header reflects the new length. The next header field of the last header of the unfragmentable part is set to 44 to indicate the fragment header presence. Figure: an IPv6 header before fragmentation. Figure: packets resulting from a fragmentation. Destination options header. The destination options header is used to carry additional information that must be processed only by the destination node or nodes, not by each node on the routing path of the packet. This kind of header is identified by a next header field value of 60. It has been decided to create only one type of header for all destination options because the next header field is limited to 8 bits and therefore only 256 values are totally available. The 8-bit next header field uses the same values as the field with the same name in the IPv4 header. The 8-bit HDREXTLEN header extension length field contains the length of the destination options header in 8-octet 64-bit units, not including the first 8 octets. The variable length options field contains one or more TLV encoded options. The only options specified by RFC 18831 that can be part of destination options header are the pad1 and the pad-n. Figure: destination options header. No next header. The value 59 in the next header field of the IPv6 header or any extension header indicates that nothing follows that header. If the payload length field of the IPv6 header indicates the presence of other octets after the header, they must be ignored and retransmitted unchanged. Security header. 2 extension headers, like the destination options header, are used to carry additional information that must be processed only by the destination node or nodes, not by each node on the routing path of the packet. These 2 headers, which are dedicated to security problems, are called the authentication header and the encapsulating security payload header. The encapsulating security payload header is indicated by the value 50 in the next header field. Internet Protocol version 6 IPv6. The effort to define a new version of IP was known as IP Next Generation or IPNG. As the work progressed, an official IP version number was assigned, so IPNG is now known as IPv6. The significance of the change to a new version of IP caused a snowball effect. The general feeling among network designers was that if you are going to make a change of this magnitude, you might as well fix as many other things in IP as possible at the same time. In addition to the need to accommodate scalable routing and addressing, some of the other wish list items for IPing were support for real-time services, security support, auto configuration, that is, the ability of hosts to automatically configure themselves with such information as their own IP address and domain name, enhanced routing functionality, including support for mobile hosts. In addition to the wish list, one absolutely non-negotiable feature for IPing was that there must be a transition plan to move from the current version of IP version 4 to the new version. Features of IPv6: addresses and routing. IPv6 provides a 128-bit address space as opposed to the 32 bits of version 4. Thus, while version 4 can potentially address 4 billion nodes, if address assignment efficiency reaches 100%, IPv6 can address 3.4 into 1038 nodes, again assuming 100% efficiency. Though 100% efficiency and address assignment is not likely, some analysis of other addressing schemes, such as those of the French and US telephone networks, as well as that of IPv4, have turned up some empirical numbers for address assignment efficiency. The IPv6 address space is predicted to provide over 1,500 addresses per square foot of the Earth's surface, which certainly seems like it should serve us all when toasters on Venus have IP addresses. Address space allocation. In IPv6, address space is subdivided in various ways based on the leading bits. The leading bits specify different uses of the IPv6 address. Table: address prefix assignment for IPv6. The entire functionality of IPv4's three main address classes A, B, and C is contained inside the everything else range. Global unicast addresses are a lot like classless IPv4 addresses, only much longer. The multicast address space is for multicast, thereby serving the same role as class D addresses in IPv4. The idea behind linked local use addresses is to enable a host to construct an address that will work on the network to which it is connected without being concerned about global uniqueness of the address. The site local use addresses are intended to allow valid addresses to be constructed on a site, example, a private corporate network that is not connected to the larger internet. Again, global uniqueness need not be an issue. Within the local unicast, address space are some important special types of addresses. A node may be assigned an IPv4 compatible IPv6 address by 0 extending a 32-bit IPv4 address to 128 bits. A node that is only capable of understanding IPv4 can be assigned an IPv4 mapped IPv6 address by prefixing the 32-bit IPv4 address with 2 bytes of all ones and then 0 extending the result to 128 bits. These two special address types have issues in the IPv4 to IPv6 transition. See the sidebar on this topic. Address notation. Just as with IPv4, there is some special notation for writing down IPv6 addresses. The standard representation is x colon 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 x, where each x is a hexadecimal representation of a 16-bit piece of address. An example would be 47CD colon 1234 colon 4422 colon AC02 colon 0022 1234 A456 0124. Any IPv6 address can be written using this notation. Since there are a few special types of IPv6 addresses, there are some special notations that may be helpful in certain circumstances. Clearly, this form of shorthand can only be used for one set of contiguous zeros in an address to avoid ambiguity. Since there are two types of IPv6 addresses that contain an embedded IPv4 address, these have their own special notation that makes extraction of the IPv4 address easier. That is, the last 32 bits are written in IPv4 notation rather than as a pair of hexadecimal numbers separated by a colon. Note that the double colon at the front indicates the leading zeros. Global unicast addresses. At the heart of the IPv6 is the unicast address allocation plan that determines how unicast addresses will be assigned to service providers, autonomous systems, networks, hosts, and routers. In fact, the address allocation plan that is proposed for IPv6 unicast addresses is extremely similar to that being deployed with CIDR in IPv4. We may think of a non-transit AS, that is, a stub or multi-homed AS, as a subscriber, and we may think of a transit AS as a provider. Furthermore, we may subdivide providers into direct and indirect. The former are directly connected to the subscribers. The latter primarily connect other providers, are not connected directly to subscribers, and are often known as backbone networks. As with CIDR, the goal of the IPv6 address allocation plan is to provide aggregation of routing information to reduce the burden on intra-domain routers. Again, the key idea is to use an address prefix, a set of contiguous bits at the most significant end of the address, to aggregate reachability information to a large number of networks and even to a large number of ASs. The main way to achieve this is to assign an address prefix to a direct provider and then for that direct provider to assign longer prefixes that begin with that prefix to its subscribers. Note that while IPv6 address assignment is essentially equivalent to the way address assignment has happened in IPv4 since the introduction of CIDR, IPv6 has the significant advantage of not having a large installed base of assigned addresses to fit into its plans. Figure: an IPv6 provider-based unicast address. The registry ID might be an identifier assigned to a European address registry with different IDs assigned to other continents or countries. Packet format. Despite the fact that IPv6 extends IPv4, its header format is actually simpler. This simplicity is due to a concerted effort to remove unnecessary functionality from the protocol. IPv6 packet data starts with the version field, which is set to 6 for IPv6. The version field is in the same place relative to the start of the header as IPv4's version field, so that the header processing software can immediately decide which header format to look for. The payload end field gives the length of the packet excluding the IPv6 header measured in bytes. The next header file cleverly replaces both the IP options and the protocol field of IPv4. If there are no special headers, the next header field is the demux key identifying the higher level protocol running over IP, example TCP or UDP, that is, it serves the same purposes as the IPv4 protocol field. Also, fragmentation is now handled as an optional header, which means that the fragmentation related fields of IPv4 are not included in the IPv6 header. The hop limit field is simply the TTL of IPv4 renamed to reflect the way it is actually used. The bulk of the header is taken up with the source and destination addresses, each of which is 16 bytes, 128 bits long. Thus, the IPv6 header is always 40 bytes long. Considering that IPv6 addresses are 4 times longer than those of IPv4, this compares quite well with the IPv4 header, which is 20 bytes long in the absence of options. The way that IPv6 handles options is quite an improvement over IPv4. In IPv4, if any options were present, every router had to parse the entire options field to see if any of the options were relevant. This is because the options were all buried at the end of the IP header as an unordered collection of type, length, value tuples. In contrast, IPv6 treats options as extension headers that must, if present, appear in a specific order. This means that each router can quickly determine if any of the options are relevant to it. In most cases, this will not be. Usually, this can be determined by just looking at the next header field. The end result is that option processing is much more efficient in IPv6, which is an important factor in router performance. The new formatting of options as extension headers means that they can be of arbitrary length, whereas in IPv4 they were limited to 44 bytes at most. Each option has its own type of extension header. The type of each extension header is identified by the value of the next header field in the header that precedes it, and each extension header contains a next header field to identify the header following it. The last extension header will be followed by a transport layer header, and in this case, the value of the next header field is the same as the value of the protocol field that would be in an IPv4 header. Thus, the next header field does double duty. It may either identify the type of extension header to follow, or in the last extension header, it serves as a demux key to identify the higher layer protocol running over IPv6. The next header field of the fragmentation header itself contains a value describing the header that follows it. Again, assuming no other extension headers are present, then the next header might be the TCP header, which results in next header containing the value 6, just as the protocol field would in IPv4. Figure: IPv6 fragmentation extension header. Auto configuration. Every host that is connected to the internet needs to be configured with a certain minimum amount of information, such as valid IP address, a subnet mask for the link to which it attaches, and the address of a name server. Thus, it has not been possible to unpack a new computer and connect it to the internet without some pre-configuration. One goal of IPv6, therefore, is to provide support for auto-configuration, sometimes referred to as plug-and-play operation. Auto-configuration is possible for IPv4, but it depends on the existence of a server that is configured to hand out addresses configuration information to DHCP clients. The longer address format in IPv6 helps provide a useful new form of auto-configuration called stateless auto-configuration, which does not require a server. We can subdivide the auto-configuration problem into two parts. 1. Obtain an interface ID that is unique on the link to which the host is attached. 2. Obtain the correct address prefix for this subnet. The first part turns out to be rather easy since every host on a link must have a unique link level address. Those devices that need a globally valid address depend on a router on the same link to periodically advertise the appropriate prefix for the link. Clearly, this requires that the router be configured with the correct address prefix and that this prefix to be chosen in such a way that there is enough space at the end to attach an appropriate link level address. The ability to embed link level addresses as long as 48 bits into IPv6 addresses was one of the reasons for choosing such a large address size. Not only does 128 bits allow the embedding, but it leaves plenty of space for the multi-level hierarchy of addressing. Limitations of current IP networks. Today's internet has tens of thousands of networks connected to it. Routing protocols, such as those we have just discussed, do not scale to those kind of numbers. This section looks at a variety of techniques that greatly improve scalability and that have enabled the internet to grow as far as it has. The fact that the internet has a discernible structure can be used to our advantage as we tackle the problem of scalability. We deal with two related scaling issues. The first is the scalability of routing. We need to find ways to minimize the number of network numbers that get carried around in routing protocols and stored in routing tables of routers. The second is address utilization, that is, making sure that the IP address space does not get consumed too quickly. Subnetting. The original intent of IP address was that the network part would uniquely identify exactly one physical network. It turns out that this approach has a couple of drawbacks. Imagine a large campus that has lots of internal networks and that decides to connect to the internet. For every network, no matter how small, the site needs at least a Class C network address. For any network with more than 255 hosts, you need a Class B address. The problem we observe here is address assignment inefficiency. A network with 2 nodes uses an entire Class C network address, thereby wasting 253 perfectly useful addresses. A Class B network with slightly more than 255 hosts wastes over 64,000 addresses. Assigning one network number per physical network therefore uses up the IP address space potentially much faster than we would like. While we would need to connect over 4 billion hosts to use up all the valid addresses, we only need to connect 214, about 16,000 Class B networks before that part of the address space runs out. Therefore, we would like to find some way to use the network numbers more efficiently. Assigning many network numbers has another drawback. The amount of state that is stored in a node participating in a routing protocol is proportional to the number of other nodes, and that routing in an internet consists of building up forwarding tables that tell a router how to reach different networks. Thus, the more network numbers there are in use, the bigger the forwarding table gets. Big forwarding tables add cost to routers, and they are potentially slower to search than smaller tables for a given technology, so they degrade router performance. This provides another motivation for assigning network numbers carefully. Subnetting provides an elegantly simple way to reduce the total number of network numbers that are assigned. The idea is to take a single IP network number and allocate the IP addresses with that network number to several physical networks which are now referred to as subnets. The subnets should be close to each other. This is because at a distant point in the internet, they will all look like a single network, having only one network number between them. This means that a router will only be able to select one route to reach any of the subnets, so they had better all be in the same general direction. The mechanism by which a single network number can be shared among multiple networks involves configuring all the nodes on each subnet with a subnet mask. With simple IP addresses, all hosts on the same network must have the same network number. The subnet mask enables us to introduce a subnet number. All hosts on the same physical network will have the same subnet number, which means that hosts may be on different physical networks but share a single network number. The subnet introduces another level of hierarchy into the IP address. The IP address has three parts: a network part, a subnet part, and a host part. When the host wants to send a packet to a certain IP address, the first thing it does is to perform a bitwise AND between its own subnet mask and the destination IP address. If the result equals the subnet number of the sending host, then it knows that the destination host is on the same subnet and the packet can be delivered directly over the subnet. If the results are not equal, the packet needs to be sent to a router to be forwarded to another subnet. The ARP is largely unaffected by the change in address structure. Once a host or router figures out which node it needs to deliver a packet to on one of the networks to which it is attached, it performs ARP to find the MAC address for that node if necessary. Figure: example of subnetting. Table: example forwarding table with subnetting for figure. The datagram forwarding algorithm. D. Destination IP address. For each forwarding table entry, underscore subnet number, comma subnet mask, comma next hop underscore. D1 equal to subnet mask and D. If D1 equal to subnet number, if next hop is an interface, deliver data diagram directly to destination. Else, deliver datagram to next hop, a router. Subnetting helps solve our scalability problems in two ways. First, it improves our address assignment efficiency by letting us not use up an entire class C or class B addresses every time we add up a new physical network. Second, it helps us aggregate information. From a reasonable distance, a complex collection of physical networks can be made to look like a single network so that the amount of information that the routers need to store to deliver datagrams to those networks can be reduced. Classless routing CIDR. Classless interdomain routing CIDR, pronounced CIDR, is a technique that addresses two scale concerns in the internet: the growth of backbone routing tables as more network numbers need to be stored in them, and the potential for the 32-bit IP address space to be exhausted well before the 4 billionth host is attached to the internet. We have already mentioned the problem that would cause this address space exhaustion: address assignment inefficiency. The inefficiency arises because the IP address structure with class A, B, and C addresses forces us to hand out network address space in fixed size chunks of three very different sizes. A network with two hosts need a class C address, giving an address assignment efficiency of 2 by 255 is equal to 0.78%. A network with 256 hosts needs a Class B address for an efficiency of only 256 by 65,535, that is equal to 0.39%. Even though subnetting can help us to assign addresses carefully, it does not get around the fact that any autonomous system with more than 255 hosts or an expectation of eventually having that many wants a Class B address. As it turns out, exhaustion of the IP address space centers on exhaustion of the Class B network numbers. One way to deal with that would seem to be saying no to any AS that request a Class B address unless they can show a need for something close to 64K addresses, and instead giving them an appropriate number of Class C addresses to cover the expected number of hosts. Since we would now be handing out address space in chunks of 256 addresses at a time, we could more accurately match the amount of address space consumed to the size of the AS. For any AS with at least 256 hosts, we can guarantee an address utilization of at least 50% and typically much more. This solution, however, raises a problem that is at least as serious: excessive storage requirements at the routers. CIDR tries to balance the desire to minimize the number of routes that a router needs to know against the need to hand out addresses efficiently. To do this, CIDR helps us to aggregate routes. A single entry in a forwarding table is used to reach a lot of different networks. This is done by breaking the rigid boundaries between address classes. CIDR requires a new type of notation to represent network numbers or prefixes, as they are known because the prefixes can be of any length. The convention is to place A by X after the prefix, where X is the prefix length in bits. To represent a single Class C network number, which is 24 bits long, we would write it as 192.4.16/24. The network numbers that are carried out in such a routing protocol are represented simply by length value pairs, where the length gives the number of bits in the network prefix. Representing a network address in this way is similar to the mask, value approach used in subnetting. We use subnetting to share one address among multiple physical networks, while CIDR aims to collapse the multiple addresses that would be assigned to a single AS onto one address. The similarity between the subnetting and CIDR is reflected in the original name for CIDR supernetting. IP forwarding revisited. In IP forwarding, we find network number in a packet and then look up that number in a forwarding table. However, CIDR means that prefixes may be of any length, from 2 to 32 bits. It is sometimes possible to have prefixes in the forwarding table that overlap, in the sense that some addresses may match more than one prefix. The task gently finding the longest match between an IP address and the variable length prefixes in a forwarding table has been a research in recent years. The most well-known algorithm uses an approach known as Patricia tree, which was actually developed well in advance of CIDR. Inter-domain routing (BGP). The basic idea behind autonomous systems is to provide an additional way to hierarchically aggregate routing information in a large internet, thus improving scalability. We now divide the routing problem into two parts. routing within a single autonomous system, and routing between autonomous systems. Since another name for autonomous system in the internet is routing domains, we refer to the two parts of the routing problem as inter-domain routing and intra-domain routing. In addition to improving scalability, the AS model decouples the intra-domain routing that takes place in one AS form that taking place in another. Thus, each AS can run whatever intra-domain routing protocols it chooses. It can even use static routes or multiple protocols if desired. The most important challenge of inter-domain routing is the need for each AS to determine its own routing policies. There have been two major inter-domain routing protocols in the recent history of the Internet. The first was the Exterior Gateway Protocol (EGP). EGP had a number of limitations, perhaps the most severe of which was that it constrained the topology of the network rather significantly. EGP basically forced a tree-like topology onto the Internet, or to be more precise, it was designed when the Internet had a tree-like topology. EGP did not allow for the topology to become more general. In this simple tree-like structure, there is a single backbone and an autonomous systems are connected only as parent and not as peers. The replacement for the EGP is the Border Gateway Protocol (BGP). BGP is also known for being rather complex. BGP assumes that the Internet is an arbitrarily interconnected set of ASs. This model is clearly general enough to accommodate non-tree structured internetworks like the simplified picture of today's multi-backbone Internet. Unlike the simple tree-structured Internet, today's Internet consists of an interconnection of multiple backbone networks. They are usually called service provider networks. We define local traffic as traffic that originates at or terminates on nodes within an AS, and transit traffic as traffic that passes through an AS. We can classify ASs into three types. Sub-AS, an AS that has only a single connection to one other AS. Such an AS will only carry local traffic. Multi-homed AS, an AS that has connections to more than one other AS but that refuses to carry transit traffic. Transit AS, an AS that has connections to more than one other AS and that is designed to carry both transit and local traffic. The goals of inter-domain routing. First, it is necessary to find some path to the intended destination that is loop-free. Second, path must be compliant with the policies of the various ASs along the path. Inter-domain focuses on a well-defined problem of optimizing the scalar cost of the path. Intra-domain focuses on finding the best non-looping policy-compliant path, a much more complex optimization problem. There are additional factors that make inter-domain routing hard. A matter of scale, an internet backbone router must be able to forward any packet destined anywhere in the internet. That means having a routing table that will provide a match for any valid IP address. The autonomous nature of the domains. Each domain may run into its own interior routing protocols and use any scheme they choose to assign metrics to paths. Inter-domain routing advertises only reachability. The concept of reachability is basically a statement that you can reach this network through this AS. This means that for inter-domain routing to pick up an optimal path is essentially impossible. The issue of trust. Provider A might be unwilling to believe certain advertisements from provider B for fear that provider B will advertise erroneous routing information. The issue of trust is closely related to the need to support complex policies. When configuring BGP, the administrator of each AS picks at least one node to be a BGP speaker, which is essentially a spokesperson for the entire AS. The BGP speaker establishes BGP sessions to other BGP speakers in other ASs. These sessions are used to exchange reachability information among ASs. In addition to the BGP speakers, the AS has one or more border gateways, which need not be the same as the speakers. The border gateways are the routers through which packets enter and leave the AS. An important job of BGP is to prevent the establishment of looping paths. It should be apparent that the AS numbers carried in BGP need to be unique. If a BGP speaker has a choice of several different routes to a destination, it will choose the best one according to its own local policies, and then that will be the route it advertises. A BGP speaker is under no obligation to advertise any route to a destination, even if it has one. This is how an AS can implement a policy of not providing transit by refusing to advertise routes to prefixes that are not contained within that AS, even if it knows how to reach them. In addition to advertising paths, BGP speakers need to be able to cancel previously advertised paths if a critical link or node on a path goes down. This is done with a form of negative advertisement known as a withdrawn route. Both positive and negative reachability information are carried in a BGP update message. The networks that are advertised in BGP are actually prefixes of any length. Thus, the updates contain both the prefix itself and its length in bits. When writing these down, it is common to write prefix/length. A final point to note is that BGP is defined to run on top of TCP, the Reliable Transport Protocol. How does all this help us to build scalable networks? First, the number of nodes participating in BGP is on the order of the number of ASs, which is much smaller than the number of networks. Second, finding a good interdomain route is only a matter of finding a path to the right border router, of which there are only a few per AS. Thus, we have neatly subdivided the routing problem into manageable parts, once again using a new level of hierarchy to increase scalability. The complexity of interdomain routing is now on the order of the number of ASs, and the complexity of intra-domain routing is on the order of the number of networks in a single AS. Integrating interdomain and intra-domain routing. How all the other routers in a domain get this information? There are several ways this problem can be addressed. Let's start with a very simple situation which is also very common. In the case of a stub AS that only connects to other ASs at a single point, the border router is clearly the only choice for all routes that are outside the AS. Such a router can inject a default route into the intra-domain routing protocol. Any network that has not been explicitly advertised in the intra-domain protocol is reachable through the border router. The next step up in complexity is to have the border routers inject specific routes they have learned from outside the AS. The final level of complexity comes in backbone networks, which learn so much routing information from BGP that it becomes too costly to inject it into the interdomain protocol. The routers in a backbone network use a variant of BGP called interior BGP (IBGP) to effectively redistribute the information that is learned by the BGP speakers at the edges of the AS to all the other routers in the AS. IBGP enables any router in the AS to learn the best border router to use when sending a packet to any address. Each router in the AS keeps track of how to get to each border router using a conventional intra-domain protocol with no injected information. By combining these two sets of information, each router in the AS is able to determine the appropriate next hop for all prefixes. Figure: example of inter-domain and intra-domain routing. All routers run IBGP and an intra-domain routing protocol. Border routers ADE also run eBGP to other ASs. Figure: BGP routing table, IGP routing table, and combined table at router B. Routing areas. Link state intra-domain routing protocols provide a means to partition a routing domain into subdomains called areas. By adding this extra level of hierarchy, we enable single domains to grow larger without overburdening the intra-domain routing protocols. An area is a set of routers that are administratively configured to exchange link state information with each other. There is one special area, the backbone area, also known as Area 0. Routers R1, R2, and R3 are members of the backbone area. These are distinct from the routers that are at the edge of an AS, which are referred to as AS border routers for clarity. All the routers in the area send link state advertisements to each other and thus develop a complete, consistent map of the area. The path of a packet that has to travel from one non-backbone area to another as being split into three parts. First, it travels from its source network to the backbone area. Then, it crosses the backbone. Then, it travels from backbone to destination network. The area border routers summarize this information and advertise it into the non-backbone areas. Thus, all routers learn how to reach all networks in their domain. Since both R1 and R2 will be advertising costs to various networks, it becomes clear as to which is the better choice as the routers in Area 2 run their shortest path algorithm. When dividing a domain into areas, the network administrator makes a trade-off between scalability and optimality of routing. The use of areas forces all the packets traveling from one area to another to go via the backbone area, even if a shorter path might have been available. An important principle in network design. This is frequently a trade-off between some sort of optimality and scalability. When hierarchy is introduced, information is hidden from some nodes in the network, hindering the ability to make perfectly optimal decisions. However, information hiding is essential to scalability since it saves all nodes from having global knowledge. It is invariably true in large networks that scalability is a more pressing design goal than perfect optimality. Processor sharing. Processor sharing is a service policy where the customers, clients, or jobs are all served simultaneously, each receiving an equal fraction of the service capacity available. In such a system, all jobs start service immediately. There is no queuing. Generalized processor sharing is a multi-class adaptation of the policy which shares service capacity according to positive weight factors to all non-empty job classes at the node, irrespective of the number of jobs of each class present. The jobs within a class form a queue, and that queue is served on a first come, first served basis, but this assumption is not necessary for many GPS applications. In processor scheduling, generalized processor sharing is an idealized scheduling algorithm that achieves perfect fairness. In multi-level processor sharing, a finite set of thresholds are defined and jobs partitioned according to how much service they have received. The lowest level, containing jobs which have received the least service, has the highest priority, and higher levels monotonically decreasing priorities. Within each level, an internal discipline is used. Quality of service. Packet switch networks support multimedia application like audio, video and data. There is more to transmitting audio and video over a network than just providing sufficient bandwidth. Applications that are sensitive to the timeliness of data is referred to as real-time applications. The distinguishing characteristic of real-time applications is that they need some sort of assurance from the network that data is likely to arrive on time for some definition of on time. A non-real-time application can use end-to-end retransmission strategy to make sure that the data arrives correctly. Such a strategy cannot provide timeliness. Retransmission only adds to total latency if data arrives late. Timely arrival must be provided by the network itself, the routers, not just at the network edges, the hosts. We need a new service model in which applications that need higher assurance can ask the network for them. The network may then respond by providing an assurance that it will do better, or perhaps by saying that it cannot promise anything better at the moment. Such a service model is a superset of the current model. Applications that are happy with best effort service should be able to use the new service model. Their requirements are just less stringent. This implies that the network will treat some packets differently from others, something that is not done in the best effort model. A network that can provide these different levels of service is often said to support quality of service (QoS). Quality of service in IP Integrated Services Architecture (ISA). Integrated Services (RSVP). The term integrated services, often called interserve for short, refers to a body of work that was produced by the IETF around 1995 to 1997. The interserve working group developed specifications of a number of service classes designed to meet the needs of some of the application types. It also defined how RSVP should be used to make reservations using these service classes. Service classes. One of the service classes is designed for intolerant applications. These applications require that a packet never arrive late. The network should guarantee that the maximum delay that any packet will experience has some specified value. The application can then set its playback point so that no packet will ever arrive after its playback time. Early arrival of packet can always be handled by buffering. This service is referred to as the guaranteed service. Other service was designed to meet the needs of tolerant adaptive applications. The service is known as controlled load and was motivated by the observation that existing applications of this type run quite well on networks that are not heavily loaded. The aim of the control load service is to emulate a lightly loaded network for those applications that request the service, even though the network as a whole may in fact be heavily loaded. Using a queuing mechanism such as WFQ to isolate the control load traffic from the other traffic, and some form of admission control to limit the total number of controlled load traffic on a link such that the load is kept reasonably low. Overview of mechanisms. In addition to describing what we want, we need to tell the network something about what we are going to inject into it, since a low bandwidth application is going to require fewer network resources than a high bandwidth application. The set of information that we provide to the network is referred to as flow spec. This name comes from the idea that a set of packets associated with a single application and that share common requirements is called a flow. When we ask the network to provide us with a particular service, the network needs to decide if it can in fact provide that service. The process of deciding when to say no is called admission control. We need a mechanism by which the users of the network and the components of the network itself exchange information such as requests for service, flow specs, and admission control decisions. This is sometimes called signaling. We refer to this process as resource reservation, and it is achieved using a resource reservation protocol. When flows and the requirements have been described and admission control decisions have been made, the network switches and routers need to meet the requirements of the flows. A key part of meeting these requirements is managing the way packets are queued and scheduled for transmission in the switches and routers. This mechanism is packet scheduling. Flow specs. There are two separate parts to the flow spec. The part that describes the flow's traffic characteristics, called the T-spec. The part that describes the service requested from the network, the R-spec. The R-spec is very service-specific and relatively easy to describe. The T-spec is a little more complicated. We need to give the network enough information about the bandwidth used by the flow to allow intelligent admission control decisions to be made. For most applications, the bandwidth is not a single number, it is something that varies constantly. Bitrate applications, such as compressed video, occasionally sends more than their average rates. If many sources send at above their average rates, then the total rate at which data arrives at the switch will be greater. This excess data will be queued before it can be sent on the link. The longer this condition persists, the longer the queue will get. Packets might have to be dropped, and even if it doesn't come to that, data sitting in the queue is being delayed. If packets are delayed long enough, the service that was requested will not be provided. One way to describe the bandwidth characteristics of sources is called a token bucket filter. Such a filter is described by two parameters, a token rate R and a bucket depth B. A single flow can be described by many different token buckets. It is good to be as explicit about the bandwidth needs of an application as possible to avoid over-allocation of resources in the network. Figure: two flows with equal average rates but different token bucket descriptions. Admission control. When some new flow wants to receive a particular level of service, admission control looks at the T-spec and R-spec of the flow and tries to decide if the desired service can be provided to the amount of traffic given the currently available resource without causing any previously admitted flow to receive worse service than it had requested. Admission control is very dependent on the type of requested service and on the queuing discipline employed in the routers. For a guaranteed service, you need to have a good algorithm to make a definite yes or no decision. For a controlled load service, the decision may be or heuristics such as admission control should not be confused with policing. The former is a per flow decision to admit a new flow or not. The latter is a function applied on a per packet basis to make sure that a flow conforms to the T-spec that was used to make the reservation. If a flow does not conform to its T-spec, then it is likely to interfere with the service provided to other flows and some corrective action must be taken. There are several options, the obvious one being to drop offending packets. However, another option would be to check if the packets really are interfering with the service of other flows. If they are not interfering, the packets could be sent on after being marked with a tag that says in effect, "This is a non-conforming packet. Drop it first if you need to drop any packets." Admission control is closely related to the important issue of policy. The reservation protocol. While connection-oriented networks have always needed some sort of setup protocol to establish the necessary virtual circuit state in the switches, connectionless networks like the Internet have had no such protocols. While there have been a number of setup protocols proposed for the Internet, the one on which most current attention is focused is called Resource Reservation Protocol (RSVP). RSVP should not detract from the robustness that we find in today's connectionless networks. Because connectionless networks rely on little or no state being stored in the network itself, it is possible for routers to crash and reboot and for links to go up and down while end-to-end connectivity is still maintained. RSVP tries to maintain this robustness by using the idea of soft state in the routers. Soft state, in contrast to the hard state found in connection-oriented networks, does not need to be explicitly deleted when it is no longer needed. Instead, it times out after some fairly short period, say a minute, if it is not periodically refreshed. RSVP aims to support multicast flows just as effectively as unicast flows. The receiver-oriented approach is adopted by RSVP. In contrast, connection-oriented networks usually leave resource reservation to the sender, just as it is normally the originator of a phone call who causes resources to be allocated in the phone network. The soft state and receiver-oriented nature of RSVP gives it a number of nice properties. It is very straightforward to increase or decrease the level of resource allocation provided to a receiver. In the event of a host crash, resources allocated by that host to a flow will naturally time out and be released. Consider the case of one sender and one receiver trying to get a reservation for traffic flowing between them. There are two things that need to happen before a receiver can make the reservation. First, the receiver needs to know what traffic the sender is likely to send so that it can make an appropriate reservation. That is, it needs to know the sender's T-spec. Second, it needs to know what path the packets will follow from sender to receiver so that it can establish a resource reservation at each router on the path. Both these requirements can be met by sending a message from sender to the receiver that contains the T-spec. Each router looks at this message called a path message as it goes past and it figures out the reservation path that will be used to send reservations from receiver back to the sender in an effort to get the reservation to each router on the path. Having received a path message, the receiver sends a reservation backup, the multicast tree, in an RESV message. Each router on the path looks at the reservation request and tries to allocate the necessary resources to satisfy it. If the reservation can be made, the RESV request is passed on to the next router. If not, an error message is returned to the receiver who made the request. If all goes well, the correct reservation is installed at every router between the sender and the receiver. As long as the receiver wants to retain the reservation, it sends the same RESV message about once every 30 seconds. What happens when a router or link fails? Routing protocols will adapt to the failure and create a new path from sender to receiver. Path messages are sent about every 30 seconds and may be sent sooner if a router detects a change in its forwarding table, so the first one after the new route stabilizes will reach the receiver over the new path. The receiver's next RESV message will follow the new path and hopefully establish a new reservation on the new path. Meanwhile, the routers that are no longer on the path will stop getting RESV messages and these reservations will time out and be released. Thus, RSVP deals quite well with changes in topology as long as routing changes are not excessively frequent. How to cope with multitask where there may be multiple senders to a group and multiple receivers. First, let's deal with multiple receivers for a single sender. As an RESV message travels up the multicast tree, it is likely to hit a piece of the tree where some other receiver's reservation has already been established. It may be the case that the resources reserved upstream of this point are adequate to serve both receivers. If there are multiple senders in the tree, receivers need to collect the T-spec from all the senders and make a reservation that is large enough to accommodate the traffic from all senders. However, this may not mean that the T-spec need to be added up. Calculating the correct overall T-spec from all the senders' T-specs is clearly application specific. Also, we may only be interested in hearing from a subset of all possible speakers. RSVP has different reservation styles to deal with such options as reserve resources for all speakers, reserve resources for any N speakers, and reserve for speakers A and B only. Figure: making reservations on a multicast tree. Packet classifying and scheduling. To deliver the requested service to the data packets, there are two things that need to be done. Associate each packet with the appropriate reservations so that it can be handled correctly, a process known as classifying packets. Manage the packets in the queues so that they receive the service that has been requested, a process known as packet scheduling. The first part is done by examining up to 5 fields in the packet: the source address, destination address, protocol number, source port, destination port. Based on this information, the packet can be placed in the appropriate class. There is a mapping from the flow-specific information in the packet header to a single class identifier that determines how the packet is handled in the queue. For guaranteed flows, this might be a one-to-one reserve mapping, while for other services, it might be many-to-one. The details of classification are closely related to the details of queue management. It should be clear that something as simple as a FIFO queue in a router will be inadequate to provide many different services and to provide different levels of delay within each service. In the case of a guaranteed service, it has been established that a weighted fair queuing discipline in which each flow gets its own individual queue with a certain share of the link will provide a guaranteed end-to-end delay bound that can readily be calculated. For control load, simpler schemes may be used. It treats all the controlled load traffic as a single aggregated flow, with the weighted for that flow being set based on the total amount of traffic admitted in the controlled load class. Scalability issues. In the best effort service model, routers in the internet store little or no state about the individual flows passing through them. Thus, as the internet grows, the only thing routers have to do to keep up with the growth is to move more bits per second and to deal with larger routing tables. But RSVP raises the possibility that every flow passing through a router might have a corresponding reservation. Admission control decisions need to be made every time such a flow requests a reservation, and some mechanisms are needed to push back on users so that they do not make arbitrarily large reservations for long periods of time. These scalability concerns have, at the time of writing, prevented the widespread deployment of INT-serve. Because of these concerns, other approaches that do not require so much per flow state have been developed. Random Early Detection (RED). A second mechanism called Random Early Detection (RED) is similar to the DEC bit scheme in that each router is programmed to monitor its own queue length, and when it detects the congestion is imminent, to notify the source to adjust its congestion window. The first is that rather than explicitly sending a congestion notification message to the source, RED is most commonly implemented such that it implicitly notifies the source of congestion by dropping one of its packets. The source is, therefore, effectively notified by the subsequent timeout or duplicate ACK. RED is designed to be used in congestion with TCP, which currently detects congestion by means of timeouts. The router drops a few packets before it has exhausted its buffer space completely, so as to cause the source to slow down, with the hope that this will mean it does not have to drop lots of packets later on. RED could easily be adapted to work with an explicit feedback scheme simply by marking a packet instead of dropping it. The second difference between RED and DEC bit is in the details of how RED decides when to drop a packet and what packet it decides to drop. To understand the basic idea, consider a simple FIFO queue. Rather than wait for the queue to become completely full and then be forced to drop each arriving packet, the trail drop policy of section 6.2.1, we could decide to drop each arriving packet with some drop probability whenever the queue length exceeds some drop level. This idea is called early random drop. The RED algorithm defines the details of how to monitor the queue length and when to drop a packet. Current implementations are close to the algorithm that follows. First, RED computers an average queue length using a weighted running average similar to the one used in the original TCP timeout computation. That is, AVG-LEN is computed as average len is equal to 1 weight into average len plus weight into sample length, where 0 less than weight less than 1 and sample length is the length of the queue when a sample measurement is made. In most software implementations, the queue length is measured every time a new packet arrives at the gate. In hardware, it might be calculated at some fixed sampling interval. The reason for using an average queue length rather than an instantaneous one is that it more accurately captures the notion of congestion. Because of the bursty nature of internet traffic, queues can become full very quickly and then become empty again. If a queue is spending most of its time empty, then it's probably not appropriate to conclude that the router is congested and to tell the host to slow down. Thus, the weighted running average calculation tries to detect long-lived congestion by filtering out short-term changes in the queue length. Second, RED has two queue length thresholds that trigger certain activity: min threshold and max threshold. When a packet arrives at the gate, RED compares the current average length with these two thresholds according to the following rules. If average length less than minimum threshold, queue the packet. If minimum threshold less than average length less than maximum threshold, calculate probability P. Drop the arriving packet with probability P. If maximum threshold less than or equal to average length, drop the arriving packet. Figure weighted running average queue length. RED thresholds on a FIFO queue. If the average queue length is smaller than the lower threshold, no action is taken. If the average queue length is larger than the upper threshold, then the packet is always dropped. If the average queue length is between the two thresholds, then the newly arriving packet is dropped with some probability P. Figure drop probability function for RED. The probability of drop increases slowly when average length is between the two thresholds, reaching maximum P at the upper threshold, at which point it jumps to unity. The rationale behind this is that if average length reaches the upper threshold, then the gentle approach, dropping a few packets, is not working and drastic measures are called for, that is, dropping all arriving packets. Temp P is equal to max P into average length minus minimum threshold divided by maximum threshold minus minimum threshold. P is equal to temp P divided by 1 minus count into temp P. Temp P is that keeps track of how many newly arriving packets have been queued, not dropped, while average length has been between the two thresholds. P increases slowly as count increases, thereby making a drop increasingly likely as the time since the last drop increases. Packet arrivals from a certain connection are likely to arrive in bursts. This clustering of drops is likely to cause multiple drops in a single connection. Only one drop per round trip time is enough to cause the connection to reduce its window size, whereas multiple drops might send it back into slow start. If a packet arrives and there is nowhere to put it, then it will have to be dropped. When this happens, RED is operating in tail drop mode. One of the goals of RED is to prevent tail drop behavior whenever possible. If the traffic is fairly bursty, then minimum threshold should be sufficiently large to allow the link utilization to be maintained at an acceptably high level. Also, the difference between the minimum threshold and maximum thresholds should be larger than the typical increase in the calculated average queue length in 1 RTT. Setting maximum threshold to twice minimum threshold seems to be a reasonable rule of thumb given the traffic mix on today's internet. In addition, since we expect the average queue length to hover between the two thresholds during periods of high load, there should be enough free buffer space above maximum threshold to absorb the natural bursts that occur in internet traffic without forcing the router to enter tail drop mode. Since RED works by sending signals to TCP flows to tell them to slow down, You might wonder what would happen if those signals are ignored. This is often called the unresponsive flow problem, and it has been a matter of concern for several years. Unresponsive flows use more than their fair share of network resources and could cause congestive collapse if they were enough, just as in the days before TCP congestion control. Weighted fairing queue, WFQ. The variation of FQ that allows a weight to be assigned to each flow queue is called weighted fair queuing, WFQ. This weight logically specifies how many bits to transmit each time the router services that queue, which effectively controls the percentage of the link's bandwidth that flow will get. With WFQ, however, one queue might have a weight of 2, a second queue might have a weight of 1, and a third queue might have a weight of 3. Assuming that each queue always contains a packet waiting to be transmitted, will get 1/3 of the available bandwidth, the second will get 1/6 of the available bandwidth, the third will get 1/2 of the available bandwidth. While we have described WFQ in terms of flow, note that it could be implemented on classes of traffic where classes are defined in some other way than the simple flows introduced at the start of this chapter. Note that a router performing WFQ must learn what weights to assign to each queue from somewhere, either by manual configuration or by some sort of signaling from the sources. In the latter case, we are moving toward a reservation-based model. Just assigning a weight to a queue provides rather a weak form of reservation because these weights are only indirectly related to the bandwidth the flow receives. Conclusion. In this chapter, we have covered the following in detail: limitations of current IP networks, Internet Protocol version 6 IPv6 features, IPv6 extension header, quality of service in IP, integrated services architecture ISA, process sharing, weighted fair queuing WFQ, random early detection RED, differentiated services.